I'm Dr. Sabna and I'm going to explain a few topics from Module 6 of Antenna and Wave Propagation for S6EC students. And the topics include radio wave propagation, modes, structure of atmosphere, as well as effect of Earth's magnetic field on ionospheric propagation. These are the contents of discussion. We are already familiar with electromagnetic waves or radio waves. They are oscillations which propagate with velocity of light, that is 3 × 10⁸ meters per second in free space. In an electromagnetic wave, electric and magnetic fields are at right angles to each other and both perpendicular to the direction of propagation. Electromagnetic waves propagate in ways that not only depend on their own properties but are also dependent on the environment itself. The actual environment in which radio waves are propagated may have obstacles, discontinuities, medium variations, etc. In recent years, radio waves have invaded outer space also. Free space do not interfere with normal radiation and propagation of radio waves. The power available at most of the receiving antennas is only a small fraction of the radiated power. The transmission loss determines whether the received signal might be useful or not. There are different modes of propagation of radio waves, and these modes will be discussed in detail. The modes of propagation depend on the frequency in use. Next, we shall see the fundamental equation for free space propagation. Consider an average power Wt assumed to be radiated isotropically in all directions. It is also assumed that the radiator is placed in free space. Radiations will spread out spherically as it travels from the source, and at a distance d, the power density will be as given: PR is equal to Wt by 4 pi d square. That is, the unit is watt per meter square. And let's assume that the directivity gain is GT. That is, it is a ratio of actual power density along the main axis of radiation of the antenna to that which would be produced by an isotropic radiator at the same distance fed with the same input power. Therefore, power density along the maximum radiation is PD is equal to GT into WT by 4 pi d square. And let's assume that a receiving antenna is positioned to receive the maximum power, and let WR be the power received and AE be the effective aperture area. Therefore, WR is equal to AE into PD, which is equal to GTWT into AE by 4 pi d square. And we also know that there is a relation between the maximum directivity gain and effective area, that is G is equal to 4 pi AE by lambda square. Okay, so therefore we can write GR is equal to 4 pi AE by lambda square, where lambda is the wavelength that is being radiated, and therefore we can write AE as GR into lambda square by 4 pi, and therefore substituting this value of AE in the previous expression, we can write WR as GTWT by 4 pi d square into GR lambda square by 4 pi. Therefore, we can write the ratio of WR to WT, that is the received power to the radiated power, which is equal to GTGR into lambda by 4 pi d the whole square watts. So this is the fundamental equation for free space transmission or propagation. This is also called Friis free space equation, where WR is equal to received power, WT is the radiated power, GT is the maximum directivity gain of the transmitter, GR maximum directivity gain of receiver, lambda is the wavelength in meters, and D is the distance in meter. It is often required to know the electric field strength of the wave at the receiving antenna. By Poynting theorem, we already know P equal to E cross H, and we know the relation between E and H. E by H is equal to eta, which is equal to 120 pi. Those two relations we already know. Therefore, we can write PD, that is the power density along the maximum radiation, PD as E square by eta, where E equal to root of PD into eta. And from the previous slides, we can write PD as GTWT by 4 pi d square. Therefore, we can simplify, and finally we get the expression for E as square root of 30 GTWT divided by D volts per meters. This is the fundamental equation which gives the field strength at the receiving antenna for free space propagation conditions. Next, we shall see different modes of propagation. The radio waves from the transmitting antenna may reach the receiving antenna through any of the following modes of propagation, depending on several factors like frequency of operation, distance between transmitting and receiving antenna, etc. The different modes of propagation are: first one, ground wave or surface wave propagation; second one, sky wave or ionospheric propagation; and third one, space wave propagation. All these will be discussed in detail in the following slides. First, we shall see about ground waves or surface wave propagation. It's of practical importance at lower frequencies, that is for medium waves, long waves and very long waves. Ground wave is guided along the surface of the earth. This mode of propagation exists when transmitting and receiving antenna are close to the surface of earth. While passing over the surface of earth, the surface wave loses some of its energy by absorption. The ground wave thus suffers varying amount of attenuation while propagating along the curvature of earth, depending upon the frequency, surface irregularities, permittivity, conductivity, etc. Earth's attenuation increases as frequency increases, and hence this mode of propagation is suitable for low and medium frequencies, that is up to 2 MHz only. Next, about sky wave or ionospheric wave propagation for frequencies between 2 MHz to 30 MHz. Sky waves are of practical importance at medium and high frequencies for very long distance radio communication. Electromagnetic waves reach the receiving point after reflection from ionized region in the upper atmosphere, which is called the ionosphere, situated between 50 km to 400 km above the Earth's surface under favorable conditions. We can see this in figure in slide number 7. Ionosphere acts like a reflecting surface and is able to reflect back electromagnetic waves of frequencies between 2 MHz to 30 MHz. Electromagnetic waves of frequency above 30 MHz are not reflected back from the ionosphere, rather they penetrate it. This mode of propagation is also called shortwave propagation or ionospheric propagation, also called point-to-point communication or propagation, since long distance point-to-point communication is possible using ionospheric propagation. Extremely long distance, that is round the globe communication, is also possible with multiple reflections of sky wave. Signals received due to sky wave propagation are subjected to fading, that is a large number of waves are received which traveled different paths, hence provision to overcome fading has to be made use of. Next, about space wave propagation, that is for frequencies above 30 MHz. VHF and UHF bands as well as communication like TV, FM, etc. utilize this mode of propagation. In this mode of propagation, electromagnetic waves travel from transmitter antenna to the receiver antenna either directly or after reflections from the ground in Earth's tropospheric region, and troposphere is that portion of atmosphere which extends up to 16 km from the surface of Earth. Thus, space wave consists of at least two components, that is direct component and indirect or ground reflected component, as seen in the figure. Since we have ground reflected component, phase change may be introduced due to reflection at the ground. Thus, direct and indirect components reach the receiving antenna either in phase or out of phase, and the strength of the resultant wave at the receiving point may be stronger or weaker. And this mode of propagation is also called tropospheric or line of sight propagation, since this mode is limited to the line of sight distance and also limited by the curvature of Earth. The line of sight distance, that is range of communication, can also be increased by increasing the height of transmitter and receiver antennas, and thus we can conclude that, as seen from the figure, the curvature of Earth as well as the height of the transmitter and receiver antennas determines maximum range of communication. Next, about tropospheric scatter propagation or forward scatter propagation for frequencies above 300 MHz. These signals were found to be propagated much beyond the line of sight propagation through forward scattering in the tropospheric irregularities. This is also known as troposcatter. It is also possible to achieve a reliable communication over a range of 160 kilometers to 1600 kilometers using high power transmitter and high gain antennas. The physical mechanism is not yet completely known, but there are two different theories involved. First one is ionospheric and is believed to be resulted from scattering of radio waves from lower E layer of the ionosphere. And the second mode is tropospheric and is thought to be result of scattering from either blobs or fine layers in the troposphere. Figure shows two directional transmitting and receiving antennas so pointed that their beams intersect midway between them above the horizon. Sufficient energy will be directed towards the receiving antenna, and this scatter propagation happens when blobs of air masses or eddies are situated in the common volume facing transmitter and receiver antenna beams. When the wavelength is more than the eddies, scattering may occur in all directions, even some backscattering also. But when the wavelength is smaller, forward scattering dominates. But we have undesirable noise and fading, and it has to be minimized by diversity reception techniques. Next, about the structure of atmosphere. Since the medium between transmitter and receiver antenna plays an important role, it is necessary to study the medium above Earth's surface. The main important regions are, first one, troposphere, which extends for up to about 15 kilometers from the surface of Earth. Then comes ionosphere, which exists from 50 kilometers to 400 kilometers above the Earth's surface. And finally, we have outer atmosphere, which is above 400 kilometers from the Earth's surface. First, about structure of troposphere. It is that portion of Earth's atmosphere which extends from Earth's surface up to a height of 8 to 10 kilometers at poles and up to 16 to 18 kilometers at equator. On average, we can say that troposphere extends up to a height of 15 kilometers from the surface of Earth. In troposphere, water vapor components sharply decrease with increase in height. Also, temperature decreases with increase in height. Next, about ionosphere. The upper part of atmosphere where ionization is appreciable is known as ionosphere. It absorbs large quantities of radiant energy from sun, which heats up the atmosphere and also produces ionizations, that is, formation of positive and negative ions. The ionized region thus consists of free electrons, positive ions as well as negative ions. Most important ionizing agents are UV rays, alpha, beta rays, cosmic rays, etc. Under very low pressure, it is possible to knock off 1 or 2 electrons out of a gas molecule. Thus, at high atmosphere, conditions for ionization are very much favorable, as pressure is low and sun is constantly radiating UV rays. The ions, electrons and atoms in a gas are constantly in motion, so frequent collisions occurs, resulting in recombination as well. In the lower part of Earth's atmosphere, collisions are very frequent and hence air molecules do not remain ionized for a longer time. Also, UV rays from sun are greatly absorbed by the upper parts of atmosphere, so that there is relatively little ionization in the lower part of Earth's atmosphere and very little ionization below about 50 kilometers. Above 400 kilometers, air particles present are so few that the density of ionization is again very low. Therefore, considerable ionization exists in the intermediate height, that is between 50 kilometers to 400 kilometers, and this region has most influence on sky wave propagation. Next, about different layers of ionosphere. Ionosphere has several layers. Different layers are due to the fact that different gases are ionized at different pressures, that is different heights, and there are different ionizing agents. The levels at which electron density, because of ionization at different pressures and due to different agents, reaches a maximum are called layers. The number of layers, their height, amount of sky wave that can be bent by them will vary from day to day, month to month and year to year. For each layer, there is a critical frequency above which, if a radio wave is sent vertically upward, will not return back to the earth but will penetrate it. During daytime, there are 3 principal layers, that is E, F1 and F2, and besides these regular layers, there is a D layer which is below E layer. and during night time D layer vanishes, F1 and F2 combine to form one layer, that is called F layer. Hence at night only two principal layers, that is E layer and F layer. Next, about characteristics of different regions, that is first one D region, which is the lowermost region of ionosphere, and its height ranges from 50 kilometers to 90 kilometers. It is present only during daytime and disappears at night. It is believed to be ionized by photoionization of NO, which prevails at that height. Ionization is produced by L alpha, that is Lyman alpha radiation from the sun. It is capable of reflecting very low frequency signals as well as low frequency signals, and absorbs to certain extent medium frequency and high frequency signals, and critical frequency is about 100 kilohertz. Next, about E region. It is above D region and its height ranges from 90 kilometers to 140 kilometers, having maximum density at 110 kilometers. Two scientists, that is A.E.Kennelly from USA and Oliver Heaviside from England, independently predicted the existence of this layer in 1902, and hence this layer is also called Kennelly Heaviside layer. Critical frequency lies in the range 3 MHz to 5 MHz. E region is formed by ionization of all gases by soft X-rays. And next, about F region or Appleton region. The region of ionosphere lying between 140 kilometers to 400 kilometers from Earth's surface is called F region or F layer, and its average height is around 270 kilometers. It is the uppermost ionized region and is the only region which always remains ionized irrespective of hours of day or seasons of year. In 1925, Appleton showed that there was a further densely ionized layer at a still greater height than E layer. He concluded this by hearing echo effects by sending short duration high frequency signals projected vertically upwards. Hence this layer is also called Appleton layer after the discoverer. Being topmost layer, it is highly ionized and hence some ionizations remain even after sunset. Therefore, F region facilitates long distance propagation of radio signals even during night hours. During daytime, this region is split into two layers called F1 and F2 layers. Next, about characteristics of F1 layer, range from 140 kilometers to 250 kilometers and average height at 220 kilometers. Critical frequency of the order of 5 MHz to 7 MHz. It is believed to be formed by ionization of oxygen atoms. Then next, about F2 layer, height ranges from about 250 kilometers to 400 kilometers. Have highest electron density of all the ionospheric layers, and formed by ionization of UV rays, X-rays and corpuscular radiations. Critical frequency is 10 MHz and ranges from 5 MHz to 12 MHz. And finally, we have the outer atmosphere or G region. It is the region further away from 400 kilometers. Moving on to the last topic of this discussion, effect of Earth's magnetic field on ionospheric propagation. A radio wave propagating in an atmosphere which is not ionized is not affected by the Earth's magnetic field, but in an ionized medium, that is ionosphere, electrons are set in motion by electric field of the radio wave, and then Earth's magnetic field exerts a force on vibrating electrons, producing twisting effect on their paths. The Earth's magnetic field splits up incident radio waves into two components, ordinary waves as well as extraordinary waves. The two rays are bent different amounts by the ionosphere and hence travel through it along slightly different paths. The rates of energy absorption and velocities also differ. The phenomenon of splitting of wave into two different components by Earth's magnetic field is called magneto-ionic splitting. The Earth's magnetic field also affects the polarization of the incident wave. The electron motion is now modified into an elliptical or spiral motion by Earth's magnetic field, as shown in figure.
The Earth's magnetic field causes electrons and ions in ionosphere to trace complicated trajectory, the frequency of which depends on magnetic field and E by M ratio, charge to mass ratio of the particle. This frequency is about 1.4 MHz and is called gyro-frequency Fg. It is defined as a frequency whose period is equal to the period of the revolution of an electron in its circular orbit under the influence of Earth's magnetic field. The expression for Fg is given as Fg is equal to B into E by 2 pi m. If the frequency of incident radio wave is equal to the gyro frequency, or if it is close to the gyro frequency, then there is a resonance phenomenon and the oscillating electron receive more and more energy from the incident wave. As a consequence, their velocity increases and they describe larger and larger orbit as seen in figure B in the previous slide. Hence, they have more and more chances of having inelastic collisions and thereby dissipate large amount of energy from the incident radio waves. Hence, attenuation is maximum near gyro frequency. Beyond the frequency of about 2 MHz, attenuation is small and hence can be used for communication. Similarly, at lower frequencies, when F less than Fg, electrons vibrate in smaller loops, usually making several loops, and the polarization is not affected much. These are my references, and thanks a lot for your patient listening.